welcome everyone to Iris Biotech's third online workshop. True to our slogan, empowering peptide innovation, we are keen on knowledge exchange and getting in contact with scientists all over the world, which is why we started the Iris Biotech workshop series mid of this year. Today, our main topic are cysteine protecting groups, surrounded by some brief introductory information on the company Iris Biotech itself. My name is Karin Rustler and I'm working as a project manager at Iris Biotech, and today I will guide you through this online workshop. If you wish to announce your participation on social media, please feel free to use the hashtag Iris Workshop Series, which is also displayed in the Microsoft Teams chat right now. To have a pleasant experience for all participants, I would like to begin with some technical guidelines. To ensure the best possible audio and video quality, all participants are automatically muted and your video camera is switched off. Another important information is that this live event is recorded. Thus, if you enter late or miss anything, please check on the bottom left side of your Teams screen if you are watching the recording or if you are in the live session. You have the possibility to pause the video, rewind, or jump back to the live session. In addition, the recording of the workshop will be uploaded to our website afterwards. Questions can be submitted by using the Q&A chat of Microsoft Teams. You can either enter your name or submit your question anonymous, just as you prefer. We will frequently check the questions, publish them, and submit them to the respective speaker. If you have any technical queries, you can also submit them in this Q&A chat, and our technical assistant will then connect with you and try to solve the problem. Initially, the questions are just visible for the organizers and will then be published to the audience. So don't worry if your question takes a short moment to appear. To try out the Q&A chat, we will now post a question which you can answer. So now you should see the question, who is today's external guest speaker within the chat and also displayed in Microsoft Teams. So please feel free to answer the question to try out the Q&A chat. So let's see if answers are coming in. Who is today's external guest speaker? No answers so far. Okay, and now I see we got one answer, and of course, yes, today's external guest speaker is Professor Fernando Albericio. So the Q&A chat seems to work. So I would like to quickly give you an overview on today's agenda. We will start with a short company and topic introduction by our project manager, Dr. Markus Weishaupt. Afterwards, our external speaker, as you know, Professor Fernando Albericio, will provide detailed information on cysteine protecting groups. As mentioned, questions will be collected throughout all talks in the Q&A chat and are then forwarded to the speakers. Of course, if you have a question afterwards, feel free to contact us or the speakers directly via email. And one last note from my side before we start, if you accidentally close your Microsoft Teams window, please don't panic. You can just easily re-log in by using the same link as you just did. So after this quick technical introduction, let's continue with the first agenda point, an introduction to our company and the topic cysteine protecting groups by our project manager, Dr. Markus Weishaupt. Markus studied biochemistry at the University of Bayreuth and obtained his PhD at the Max Planck Institute in Berlin in the field of solid phase organic synthesis. In 2015, he joined Iris Biotech as a project manager. So Markus, thanks for your valuable time and please go ahead with your presentation.
So thank you, Karin, for the kind introduction. I hope everybody can see the presentation. So as Karin mentioned, I would like to give a brief introductory presentation regarding cysteines and cysteine protecting groups. But first of all, let me briefly say a few words about our company, Iris Biotech, for those of you who don't know us yet. Iris Biotech was founded in the year 2001, so this year actually marks our 20th anniversary. Our roots go back to the year 1788 to the chemical factory Marktredwitz, which is in fact the very first chemical factory in Germany. Nowadays, Iris Biotech has its own production site in Germany, as well as production partners mainly focused in Europe and Northern America. We also have a net of worldwide distribution partners to give us a global footprint. Although we are best known as a provider for anything related to peptide chemistry, our portfolio, which now comprises around 7,000 products, is actually quite diverse. It contains compounds from categories as diverse as life sciences, linkerology, or drug delivery, to name just a few. True to our motto, empowering peptide innovation, in our bi-weekly newsletter, we inform our clients about the latest product additions and additional noteworthy news. Our newsletter blog posts and booklets on various topics can be found in the knowledge base of our website. Part of our philosophy is to provide compounds from lab scales or gram quantities through pilot scale up to bulk quantities for commercial productions. So with this, let's continue to the chemical part of this introduction. So as is probably common knowledge, cysteine is one of the rarest amino acids in human proteins. In spite of this, cysteine is essential for the function of many proteins. It may be part of active sites, for example, in cysteine proteases. It may be coordinating structural or catalytic metal ions, the most common being zinc. And it can also be important for the three-dimensional structure and thus the biological activity of peptides and proteins that contain disulfide bonds. In the fields of ligation and conjugation, of course, cysteine is the key residue in the classical native chemical ligation and is also frequently used for malimete thiol conjugation chemistry. Due to its intrinsic properties, there are some synthetic considerations to take into account. Cysteine is prone to oxidation as well as to racemization. If the target compound contains more than 3 cysteines, there's the possibility of incorrect disulfide bond formation and also disulfide shuffling. So special care is warranted in the synthesis of both cysteine building blocks and cysteine-containing peptides. So as there are already some or quite a number of cysteine protecting groups on the market, you may ask why add more? So one reason is that some of the existing protecting groups have their own drawbacks. For example, the commonly used trityl and MMT protecting groups, when used in the same peptide synthesis, are not fully orthogonal to each other. When MMT is cleaved with 1% TFA, there already occurs a partial loss of trityl. The commonly used ACM group is known for side reactions that occur during deprotection, which of course then complicates final purification. The ester-butyl group, on the other hand, may take a long time to deprotect if it comes off at all. So clearly, the addition of new innovative cysteine protecting groups is warranted. At Iris Biotech, we have worked also with academia on expanding the arsenal of cysteine protecting groups. One such protecting group is the MSBH group, which Iris Biotech actually commercialized. Before that, it was only known in academic circles. So how does it look like? Structurally, MSBH is a benzodryl protecting group with two methylsulfonyl groups. Those exhibit an electron withdrawing effect, thus rendering a potential carbocation at this benzylic position unstable. So consequently, this sulfur carbon bond here is stable towards acids and bases. When the sulfonyl groups are reduced to the corresponding sulfide groups, this effect is inversed, thus making or rendering this sulfur carbon bond here acid labile. Consequently, MSBH can then be cleaved with, for example, TFA and an appropriate scavenger. So due to these properties, when in its original oxidized or non-reduced state, the MSBH group is stable to conditions used in the FMOC protocol, in the BOC protocol, and also in the allyl strategy. It can be removed selectively and under mild conditions with ammonium iodide and, for example, TFA as an acid. So to briefly sum up, cysteines are essential for the biological activity of many peptides and proteins. However, they may pose considerable synthetic challenges. New sophisticated cysteine protecting groups are required to overcome those challenges. Here are some cysteine protecting groups, like the aforementioned FMOC, L-cysteine MSBH, a building block here, and others that you may see in the following presentation. And all of those are, of course, available from Iris Biotech. If you want to learn more about cysteine protecting groups, and also the synthesis of cyclic peptides in general, I recommend that you download this brochure, Novel Strategies for the Synthesis of Cyclic Peptides, which is available free of charge from our website, alongside many other interesting booklets. So with this, I would like to thank you for your kind attention, and if there are any questions, I would be happy to answer them.
So thank you, Markus, for giving this talk. Yeah, we have already one question, and this one is, do the deep protection conditions for MSBH affect already formed disulfide bonds? Can you comment on this one?
Yes, so there's a paper that was published in Angewandte Chemie in 2014 by the Aylward group, in which the synthesis of human hepcidine is described. This is peptide containing 4 disulfide bonds, and the cysteines that are protected with MSBH are deblocked or deprotected after all the other 3 disulfide bonds have already been formed. So the deprotection conditions for the MSBH did not affect the existing disulfide bonds.
Okay, so thanks for your answer. So far, I see no further questions. Please, to all participants, be aware that there is a slight delay between submission of the question and appearance. But if there are any questions which are still in the waiting line and we are not answering right now, we will come back to those ones later. So after the introduction, let's go ahead with our highlight and switch to our external guest speaker. It's a pleasure to introduce to you Professor Fernando Albericio. Fernando is research professor at the University of KwaZulu-Natal in South Africa and full professor at the University of Barcelona in Spain. His major research interests cover practically all methodological aspects of peptide synthesis, like coupling reagents, protecting groups, resins, as well as synthesis of peptides and small molecules with therapeutic activities, mainly in the field of cancer and infectious diseases. He has published over 1,000 scientific papers and co-authored 4 books. He has filed more than 60 patents. He is editor-in-chief of several scientific journals, and he is acting in the editorial board of several others. Besides, he also received several awards. So, Fernando, it's really an honor for us to have you with us. And yeah, I see that you might still be muted. So please just unmute yourself, and yeah, we are looking forward to your presentation.
Thank you very much, Karim. I think Marcus has to remove to share, or I need to share myself.
Yeah, you can start sharing your presentation.
I'm not sure if I can share my presentation because it's Marcus is the.
Let's see, maybe just quickly ask our technical guide,
Yes.
Klaus. Does it work to share the presentation of Fernando, Klaus?
I can't see it yet.
Okay, so Fernando, I think.
Okay, yeah, you're
Yep.
right.
Okay, perfect. Yeah.
Now I can see it.
Yes, sorry.
Great, no
Let
problem
me
at all.
put full screen.
Exactly.
And finally, let me look for the pointer. Okay. Again, thank you very much to Karim, to Marcus, to Klaus, to Thomas. It's a real pleasure for us, for me, to be here with you this afternoon, this morning in USA, and this evening, night in India, because I know that some people in India is connecting us. Of course, peptides are my life, but cysteine is an important part of my life. Maybe I devoted many years, efforts to work on cysteine. And for me, it's a pleasure to share with you our last findings in cysteine protecting groups. This is an analysis that every year Beatriz and I doing on the new drugs accepted by the FDA, and in the 2016-2020 FDA drugs accepted, there are totally 228 new drugs, and 14 of these new drugs, around 7-8%, are peptides. But this 2020-2021 year is wonderful. Only in this year so far, okay, we are very close to the end of the year, we have 8 new peptides. This means that in the next year will be a total about 280 new drugs, and 22 will be peptides, will be 8-9% of all drugs accepted by the FDA are peptides. This means that our field is increasing, our field is very powerful. Peptide synthesis, in just a sentence, is a right combination of coupling reagents and protecting groups. So easy and so complicated at the same time. About coupling reagents, I am working a lot in collaboration also with Luxembourg Biotechnologies, with IDIS, in developing several of them. As you can see, our favorites are Oximapure in combination with DIC, Pioxim, and COM. About protecting groups, this is a chart of the different proteinogenic amino acids, and there are 2 in yellow. These 2 in yellow are because they contain sulfur. And from these 2, cysteine is probably one of my favorites. I started to work during my PhD in the synthesis of a cysteine containing peptide, was apamine, and continue doing the years. Cysteine, as Marcus highlighted, there are so many flavors of cysteine protecting groups, but I have to share with you that there are also so delicious, all these different flavors of the cysteine protecting groups. A little bit, I will repeat one of the slides of Marcus. This is the wall of the cysteine. It's not only about peptides containing disulfide bridges, but also we have nice peptides. They are thioether, chemical ligation, bioconjugation, thiolactone peptides, just a single cycle with a thioester, and also cysteine is very useful for the synthesis of maps of multi-antigenic peptides. A real world around cysteine. There are three approaches to prepare disulfide bridges. The first approach, PG1 protecting group 1, protecting group 2 can be the same or can be different. Both are deblocking at the same time with the free thiols, and then we carry it out an oxidation. In the approach 2, we have again 1 or 2 protecting groups, but in that case we make a oxidative removal and directly we are getting the disulfide bridge. And the third approach, and it's for us the best one, and it's very, I will show some examples today. We have 2 different protecting groups. In one case, we selectively develop one of them. In another one, maybe you have to activate it, or maybe it's still activated. Today we'll see an example that is already activated, and then there is a nucleophilic attack of the sulfur minus to the sulfur that is activated plus to form the disulfide bridge. But about the formation of the oxidation, one of the most popular methods is iodine. But iodine is very often difficult to handle and sometimes very often lead to over-oxidation. With Tobias in Barcelona a few years ago, we developed the N-closoxynimide. N-closoxynimide is also a mild oxidative reagent. We can have in solution, is a solid, is a good alternative to iodine, is a solid, and is soluble in a broad range of solvents. From water to water acetonitrile, very convenient for peptides, to DMF, very convenient to make this oxidation on solid phase. But also, we were able to prepare a supported resin with N-closoxynimide. We prefer to use ChemMatrix as supported resin because ChemMatrix, again, is compatible with water acetonitrile, and with DMF. But of course, we can use other solid support as polystyrene. NCS can oxidize peptide solution or while the peptide is still encoded on the solid support. And the resin, of course, only can oxidize peptide in solution. Oxidation takes about 10-15 minutes using 1 or 2 equivalents of NCS. The workup is very easy. The side products N-hydroxysuccinimide, and it's much difficult to get over-oxidation as happens with the iodine. This is one example of that. This is one example of the, I think is one of the gonotoxin. Yes, we have on the resin 2 disulfide bridges already free. We have NCS 2 equivalents 15 minutes. We have the first disulfide. We have the second pair of cysteines protected with methoxytritol, and we remove 2% TFA, and we can perform the second oxidation in 15 minutes. And we have at the end the final product with a more than decent purity, and everything, the stepwise synthesis and both oxidations have been done on the resin. The first protecting group that I will talk is a dual concept, is the pseudoprolines. Pseudoprolines was developed by Thomas Hack in the group of Manfred Matter in Switzerland many years ago, and they are very popular from serine but also from cysteine to minimize aggregation, to break interaction between the chains, and to facilitate the stepwise synthesis. But in the case of this, but also they can have 2 interesting properties. One can enhance cyclization, and in another hand, as the cysteine derivative, the cysteine pseudoproline is more stable than the SER and the threonine pseudoproline, we can use the cysteine pseudoproline as a building block to restrict conformation, to prepare cyclic peptides with a restricted conformation. The removal of the cysteine in linear sequence could be removed. It's taking very often several hours, sometimes 36 hours, 2 days, but can be removed. The cyclic sequence are much more difficult to remove and have to use TFMSA, trifluorometanosulfonic acid, or even HF. Here we have an example. We tried to make a conotoxin that one of the disulfide was substituted by a lactam. Here we have our sequence of the conotoxin. One of the cysteine is protected with either trityl or the pseudoproline, and the second is protected with trityl, but the idea is to make the cyclization with the side chain of the carboxylic acid of the aspartic and the amine group of the diaminopropionic acid. We make the cyclization on the resin with Dic oxima pure, and we are getting here the results. One, we are doing in 2 cases. Also, we play with a little bit the hindrance of this amino acid. One, the protecting group of the cysteine is the pseudoproline. As examples 1 and example 3, you can see the cyclization take place with quantitative results. We have the anhydrine, and the anhydrine is totally clear. It's totally clear. But when this cysteine is protected with the trityl, example 2 and example 4, in that case you can see very clear that the anhydrine is still positive. This means that the pseudoproline helped us to perform the cyclization, and this is really important to have a nice final product. Of course, when we can remove this final product, probably the dimethyl pseudoproline is not the best choice, but also IDIS Biotech has in his catalog the dimethoxybenzyl pseudoproline. I will show right now one example of the use of the pseudoproline as a building block. A few years ago, we started a project in collaboration with a company, PharmaMar, to synthesize several analogs of paclitaxel 19. This is a natural product from the marine and was with some biological activity against cancer. They have 3 products. It's a cyclic peptide with 3 products. I give this project to one of our best PhD students, Marta Pelay, and she developed a synthesis, a normal synthesis. He prepared the natural product. He was the natural product. He prepared the synthetic with the same sequence of the natural, and he coeluted, and we have just a single peak. You can see that the gradient was very slow, from 35 to 55%, to be sure that we are able if we have 1 or 2 products. We have just 1 product. Both products were exactly, but when we study the activity of these 2 products, we realized that the natural was active and the synthetic was not active. Even we prepared a small library with playing with the methoxyprolines, and any of these compounds were active again. This was to make it short a long history. We decided then to substitute the different prolines by this dimethyl pseudoproline. We prepared 7 analogs. We substitute 1 by 1, 3 with mono substitution, 3 with 2 substitution, and 1 with the 3 substitution. The synthesis of this was a little bit more difficult, but we were able to get some activity. Means the introduction of these restricted amino acids, these dimethyl thioprolines, was making this peptide more rigid and was giving activity our final product. For instance, here we have an example that we substituted 1 proline by 1 dimethyl thioproline. And you can see in the NMR of this compound that we have several conformers, and 4 of these are important conformers. When we did the same experiment with our final product, the one have more activity with the substitution of 3 prolines, we realized that we have a major conformer. Means again, This is an excellent building block to prepare conformational restricted cyclic peptides. To find acyl-lipoyl cysteine protecting groups is a long history. We have a paper of 1962 from Leonidas Servas. Leonidas Servas was the same that discovered the Z group, Z from Servas, and he's saying that boiling trifluoroacetic acid, converts triethylcysteine very easily in cysteine. We know right now, 60 years later, that we don't know to boil trifluoroacetic acid. We need only a few percent of trifluoroacetic acid, but with the correct scavenger. This is the importance of the scavengers in all of the cysteine chemistry. Here is an example from my previous topic, this pseudoproline, and here we have a peptide with a pseudoproline, and we were able, in that case, was a simple peptide, we were able to remove this pseudoproline with 95% TFA, 2.5% TIS, trisopropylsilane, and 2.5% water. But if we miss the TIS, if we put only TFA and you put only TFA and water, we see that the triethyl of the cysteine and the triethyl of glutamine are back alkylated, the two cysteines. Means the only difference between one experiment and another experiment is in the second we miss the trisopropylsilane as a scavenger. To take home, it's very important to use the right scavenger in all cysteine chemistry. Here was most of the protecting group was available from IRIS, or some of them were in the past commercially available. MMT, the methoxytriethyl, you can remove 0.1% TFA, the 4-methyltriethyl 1% TFA, xantenil also 1%, TMOP, and we developed with George Badani about 5% TFA, triethyl about 25% TFA, and then we have the paramethoxy benzyl or MOP, then we need 95% TFA plus the 40 degrees HF. Means it's clear this is a gap, and we need a protecting group that we can remove with 60-70% of TFA. Then will be totally compatible with MMT. Means similar to the BOC. Means we have, for instance, the triethyl can protect the lysine removal with 1 or 2%, or the BOC can protect the glycine and is removed with 40-50%. This is the case. We need a cysteine protecting group that can be removed in 60-70% of TFA. With Miriam Góngora in the laboratory, she did a real also with Ivan Ramos Tomillero. They did an excellent screening, and with benzyl derivative, they came that the 2,6-dimethoxy was fulfilling our ideas. And also the 2-methyl-4-methoxy. The rest, some of them is very interesting. The 2,4,6-trimethyl was totally stable to TFA, and some of them was not good enough. Also, with the benzyl system, we were able to see that the diphenyl methyl was also fulfilling our good properties. This means that we need 60% of TFA in the presence of the right scavengers. From these three, the 2,6-dimethoxybenzyl, the 4-methoxy 2-methylbenzyl, and the diphenyl methyl, we were discussing with Thomas at IRIS, and we decided that probably the winner will be diphenyl methyl because the starting product is really available and it's cheaper. Then again, we are coming back, the idea of we need the right scavenger. Just to show the compatibility of MMT, triethyl, and diphenyl methyl, we prepare this small peptide having the 3 protecting groups, and we put this peptide in the presence of some TFA. If the TFA is very strong, we'll remove the 3 protecting groups, and we'll get, then we alkylate it with methyl iodide, and then we will get the 3-methyl derivative. If the side chain, the TFA is not very strong, we'll remove one or two of these protecting groups, and after alkylation, we'll get this alkylated. Using that, we can see that when we treat our peptide with 10% TFA, we are getting the dimethyl peptide. This means that the MMT and the trityl was removed, and the DPM, diphenyl methyl, was stable. When, of course, we are using 90% TFA, we are able to remove the three of them. And when we are using 60% TFA, we realize that some also we remove the three of them, but partially only two of them. Means the TPM, the diphenyl methyl, needs to be sure 90% of TFA, and with 10% of TFA, we are very safe because only MMT and trityl will be removed. This is a nice cartoon about that. MMT and trityl are not compatible, but MMT and also trityl are totally compatible with the DPM. This is one example. Here we're going to synthesize a parallel dimer. We have one cysteine protected with methoxytrityl, another cysteine protected with diphenyl methyl. We cleave with the silver resin with 5% TFA, and we are getting only one cysteine free, another with DPM. We make oxidation with dimethyl sulfoxide. We have the first disulfide bridge, and then we remove with 90% TFA. We remove the second protecting group, and we make oxidation with dimethyl sulfoxide, and we have here the parallel dimer. A little bit more complex. In that case, using also is a conotoxin analog. We have two trityls and two DPM. We cleave the peptide from the resin. We make the oxidation with ammonium hydroxide, pH 8.5. We have the first cycle, and then we treat with 90% TFA. We remove all the protecting groups, and then we make the oxidation. We make the cleavage and oxidation in this case at the same time, using also in the presence of DMSO, and we have also the final. This is the final peak. I will not talk today about the cysteine THP because we have a lot of things, but also with Ivan Ramos, Tomilledo, and Hortensia Rodriguez in Barcelona, we developed this. This is very interesting. In the future, we'll talk a little bit more. Also, it's available for IRIS, it's very important, but it's very interesting because it's very similar to trityl. You need 10–15% to remove, but think that it's not aromatic. This is very good, and also it's not reversible. Means that once it's deprotected, it cannot be anchored again to our peptide. And also, right now in South Africa, in Durban, SNI, an excellent PhD student in the laboratory, is working with this protecting group, and he's getting fabulous results, and we'll share with you in another day. And Marcus was talking about ACM. ACM is a good, the acetamidobacter is a good protecting group. To remove and to give the free trial, we need mercury and silver salts. This is not possible in the present moment. And to make the blocking oxidation at the same time, we are using iodine, or also using NCS. Means the ACM has some side products. Mark was talking, was some SN rearrangement. SO means the group can go from the cysteine to some of the lysine, can go to the tryptophan, can go to some of the tyrosine. Can modify tryptophan, tyrosine, and methionine, and also can modify the tryptophan and can give over-oxidation. In a joint collaboration, we started before about that, we changed the methyl by the phenyl, and we developed the phenyl acetamidomethyl protecting group that is orthogonal to both BOC and SMOC strategy, and is revived similarly than the ACM. You can remove with iodine, you can remove with NCS, but also you can remove by the PGA enzyme. This is one of the examples, and here we have the synthesis with the ACM, oxidation with iodine, cleavage of the peptide from the resin, and we have here the purity is about 40%. But if we are doing the same with the PHACM peptide, removal with PGA, we can see here that the removal and the oxidation, the purity of this peptide is much better. This was a joint collaboration with IRIS and also with Alessandra Basso at Purolite, and provide the enzyme. Again, I want to repeat that also, I don't have today any example, but also PHACN can be removed with iodine and can be reduced with NCS, and is giving much cleaner crude products. This is the different condition that we can use the PHACM, and we can use, of course, water, but also we can use with phosphate base in the presence of DMSO. We're using DMSO, we get directly the formation of the disulfide bridge. We are getting directly the oxidation, but we can got another organic solvents as methanol, DMF, ethylene glycol, and in that case only we will get the free thiol. This one, another beauty of this supported PGI enzyme, and you can recycle. And this is the example of one after 5 recycle cycles. This is one example of one synthesis for oxytocin. Then they have an extra cysteine for bioconjugation. The two cysteine from the oxytocin are protected with trityl, like cleave, and then we have the extra cysteine protected with PHACM. We make the oxidation with water and DMSO, 16 hours. We have the cycle of the oxytocin, and then we can remove the PHACM, and we have here the cycle of oxytocin with a free thiol to be anchored to another biomolecule or another drug. Here is the synthesis of a peptide of 18 amino acids, the T22, and again we can use 2 trityls, first oxidation, and then 2 PHACM to remove in the presence of a DMSO and have the right peptide, or even we can prepare the peptide with 4 PHACM and then to have the oxidation. The synthesis, the regioselective synthesis, the quality of the peptide is slightly better than the random strategy, but we can use both strategies. Means PHACM is an excellent substitution for ACM. Here is also for chemical decyclization using native chemical ligation. In that case, we prepare the peptide using an aspartic by side chain anchoring. When we have finished the peptide, we introduce the first aspartic protected with allyl ester. We remove the allyl ester. We introduce our glycine with a thioester. When we have this, we remove the PHACM very mild, and we perform the native chemical ligation, giving this nice cyclic peptide. Means also the PHACM is very valid for in the chemical nitric ligation if we have to protect one of the cysteines. The final example in this part is the synthesis of a very difficult peptide is thiocodalaine. Thiocodalaine we'll see in the next slide, but it's an octapeptide, it's a dimer. Then we have 3 cysteines. We have methyl cysteine, we have 2 cysteine, then N methyl cysteine is giving a disulfide bridge, and also we have one of these methyl cysteine is giving an ester with one of the with the C terminal. Okay, this was very complicated. Took us several years to reach a good strategy, but for the last cysteines that at the end will give the disulfide bridge, we choose PHACM for the protecting. For the cysteine that have to be the thioester, we use trityl. We make our first the half of the molecule using trityl and PHACM. We cleave the peptide from the resin in two steps. First of all, was a chlorotrityl resin. First of all, we cleave with 2% TFA to have the protected peptide in the cysteine with trityl and with PHACM. Then we make the global deprotection with 10% TFA to remove the trityl, and we perform the coupling of the two moieties. And we have the cyclic peptide with the two cysteine with PHACM. Then we remove the PHACM with the supported PGA in the presence of dimethyl sulfoxide, and we were able to get the final thiocoagulant. Marcus mentioned this is very important. Also, these protecting groups that can be removed by reducing agents, thiols or phosphines. The most popular reducing agent is DDT. DDT is oxidized to this 6-member ring. The good thing is the process of the DDT is some reduction of the sulfides, is absence of the mixed disulfide intermediates because everything is given the 6-member ring, is in solid form, and is high efficiency. Some contrast is the smell, are very expensive, is very prone to air oxidation, and we need at least pH 7 or slightly superior. Means the stability of this 6-member ring is the driving force to shift the equilibrium. Reins, MIT, proposed to use a dithiol coming from the aspartic acid. And this is the DTBA proposed by Reins, but Beatriz in the lab, she thought, and she had a good thought, that maybe you can use this as template and prepare a reducing agent not only soluble in water, but also soluble in organic solvents as DMF. And using aspartic acid, SNI, the same student that is working with THP, prepared this new reducing agent. She performed a poly benzylation, 2 benzyl groups we attached to the amine group and making 2 benzyl esters. Then when you have this bis ester, reduce both to the alcohol, converted alcohol to chlorines, reaction with potassium thioacetate, and finally reduction of these thioesters to the 2 thiols. This is good, better smell than DDT, also is very high efficiency, no, it's not oxidized by air, and the big advantage of this is soluble in a broad range of solvents, acetonitrile, TMF, DCM, toluene, dioxane, THF, methanol. Examples on the left, or I don't know, left of the screen, we can have here a model peptide with 2 asparagine trityl, very hindered this part, and the new reagent, the DAP-DT, free equivalence in the presence of DMF, diisopropyl and water. Water is very important. Again, we can be in a few minutes, we can remove the both protecting groups. This protecting group, I will talk later, is the DMP protecting group, the S-DMP. Here is in the middle, but also we can use this in a terminal cysteine, and again, this is the protected in blue, and this after treatment, 2 per 5 minutes, we can have the removal of this protecting group, and even when you have our C-terminal peptide as a mixed disulfide bridge with thiopropionic acid, using 2 per 5 minutes DAP can remove, and we have our thiopeptide ready for making some conjugation. Right now, in the as you probably asked me, we are never happy with your work. Babita and also excellent postdoctoral fellow in collaboration with SNI are preparing the next version of this DAP, and hopefully we'll have a very nice results very soon. Okay, right now we will concentrate in this protecting group that can be removed using reducing agents. The most popular was the ester-butyl. It's commercially available, is compatible with ester-butyl chemistry, easily bind to reducing agents, but sometimes takes 6 or 24 hours or even more, and sometimes is stable. Means his stability is sequence dependent. In that case, we need a new protecting group. And with Thomas in Barcelona, many years ago, in collaboration with this project was in collaboration also with Lonza and with IRIS, we developed the S-trimethoxyphenyl or S-dimethoxyphenyl. In that moment, we thought we were sure that was stable to 20% ppb in DMF and can be removed with 20% beta-mercaptoethanol in DMF containing 0.1 molar methylmorpholine, or also with 5% DDT in the same solvent. And we have here some examples. We have here, for instance, the synthesis, I think, is the oxytocin. We have the synthesis of oxytocin with ester-butyl. To remove the ester-butyl, we need 8 hours. To remove the SDMP, the dimethoxyphenyl or the trimethoxyphenyl, we need only 3 times 5 minutes. We have in all cases, we have the free disulfide, and then we perform in solution the oxidation with 5% DMSO, and you can see the final product. Maybe it's a little bit better with STMP on DMP, but this is not the big difference. The big difference is that a simple peptide as oxytocin, we need 8 hours to remove. I'm sorry, and have 8 hours to remove the ester-butyl, and DMP only for a few minutes. Here we have another example. We have the T22 with 4 TMPs. We can remove them and we have to make the oxidation. But TMP or DMP has problems. The synthesis is tedious and very demanding. The starting products are very expensive, and also ourselves and some of our colleagues realize there are a lack of full stability in front of 20% ppb DMF. With this in mind, we have, and this was a project led by Beatriz in laboratory, and she thought, we know that when you have, for instance, a disulfide bridge, it's very easy to reduce. When you have ester-butyl, it's much more difficult to reduce. What is the difference here in the disulfide bridge with the ester-butyl? The difference from a chemical point of view is very clear. Here we have a primary carbon, CH2, and here we have a tertiary carbon, this ester-butyl. Beatriz came with the idea, right now everyone will say, of course, using a secondary carbon. And this is the thing that she did. She proposed to have a secondary carbon and works very nicely. But, and with this in mind, we prepare, Amit, an excellent PhD student, prepared 2 derivatives. In that case, and Beatriz is a very pragmatic person, decided to go to a cheap and easy starting point. And this coming with this thiol and these 2 thiols. You can see that they are very similar. In both cases, they have a secondary carbon here. I'm sorry, is a secondary carbon here. In that case, it's cyclic, and in both cases, they have a beta branch. This is cycle and this is linear. The synthesis of this 2 protecting group was very easy with NCS minus 50 degrees, and then activation of this, and finally in the presence of ethoxysteine, and Amit was able to prepare ethoxysteine seed and ethoxysteine mod, and then we try it. The difference is one linear, another cyclic. Okay, and here we have a comparison about ester-butyl, mod the cyclic, and seed the linear. And in this peptide, in this model peptide, as you can see, after 500 minutes, the ethoxysteine with DDT in the propylethylamine, ethoxysteine terbutyl is still stable. Here in 20 minutes, or almost less, in 20 minutes with MOD is already, all MOD is removed. And here with SID, we need about 40 minutes, a little bit more of 40 minutes to remove the SID. When we did the same reaction with water. Again, take-home scavengers are important in cysteine chemistry. When we did this for the terbutyl, we need from 500 minutes, we need a little bit more than 100 minutes. For MOD was very, very fast, and with the SID was again in 20 minutes, but was almost removed. But again, as you know, reactivity is important, but also stability is important. MOD is more labile, but is more labile in the presence of DDT, but also is slightly more labile in the presence of PPD. SID is labile in the presence of DDT, excellent, but is fully stable in the presence of PPD. And our winner is the SID. Means you can see the terbutyl is stable, but it's too much stable. MOD is stable, but not fully stable, and SID is fully stable and very labile. And our winner is the SID. Here is the vasopressin, and you can see we prepare a meat prepare. We have to say a meat prepare is a very hard worker, and a meat prepare. This is the protected vasopressin with the terbutyl, the protected vasopressin with SID, and 5 minutes 3 times DDT. We can see that the vasopressin with the terbutyl, there are some terbutyl there, and when you have with the SID, all the SID protecting group are removed. And this is the last part of my talk. We'll talk with a wonderful performance of the SID. This we realized one Friday night, was very late in the lab, 7, 8 o'clock. We were working a meet, also with Beatriz and myself, and we didn't understand some of the results, but the results after some analysis was very clear. The SID is unique. It protects the cysteine in the synthesis, but at the same time, it activates this, this activates this sulfur in front of the attack of another sulfur. Means this reaction is very faster, and once we have all the sequence with one SID, we remove trityl, for instance, here, and this attacks to this sulfur, and is remove the SID, and we are getting the disulfide bleach. This is much faster than you have the two thiols. This example, the first example was with this small tetrapeptide. This when I was talking on Friday night, we didn't understand what happens, but what happens then the protected peptide, the peptide with a 1 free thiol and 1 SID was cyclization overnight, and when we put 15 molar sodium bicarbonate, in 5 minutes you have the cyclization. In the case of ester-butyl, also take place a little bit, but after 3.5 we need 4 or 5 hours in this very simple peptide. When we move something more complicated, again oxytocin with 1 MNT, I think this we prepare with the methoxytrityl, the another one with SID, perfect, stable, and when you put with 50 millimolar sodium bicarbonate, after 1 hour we have a very nice oxytocin. And finally, the last example was when we're making with somatostatinamide. In that case, we do the same, one cysteine with trityl, another cysteine with SID, perfect synthesis, and when we put this in 50 millimolar sodium bicarbonate, we were scared because we have several peaks, but we have to think that the tryptophan can give the carbamic acid. The carbamic acid, the decomposition of the carbamic acid takes time, and this was the difference intermediate. But after 1 hour and a half, we have two peaks, the somatostatin and the somatostatin carbamate, and after 24 hours, we have a nice peak of only the somatostatin. We are so excited about the results, and we are working and we are using the seed for another examples with excellent results with large peptides and natural peptides, very large sequence. And then these are our winners for acid lipoyl, trityl and methoxytrityl. If I have to decide for one, I will do methoxytrityl. THP, then I promise you we have excellent results. SNI is working on them. DPM, diphenylmethyl, and the pseudoproline as protecting group and also as building block, and the SMDH that Marcus has discussed at the beginning. Then we have, as reducing agent lipoyl, the SID, enzymatic lipoyl, the PSACM, and also IRIS have the palladium lipoyl. The one is commercial available is Allocam, but in collaboration with Ferswaki, my group also was working with the FESAM, is much better for the bulk chemistry. And finally, two photolipoyls, the NDPF, that is lipoyl, is a photolipoyl, but also by infrared, and the orthonitrovalidyl, that is photolipoyl. I think we have, and IDs are commercially available, we have an excellent winners of the Cysteine protecting group. And this is then, this is the group in South Africa. This is Amit. I have to congratulate Amit. Amit is in Bangladesh in these days because he got married after 2 weeks ago, and we congratulate him to get married and asking Amit, please come back to the lab. And this is SNI. SNI was working in the reducing agent, and also in the right now is working in the new application of the THP. This is the group in Barcelona. Hortensia right now is the Dean of Chemistry in Ecuador. Ivan around here was working. Miriam Gongola was working with also several of the protecting group. Tobias was working in the first version of the reducing agent. And again, I think that's all. Thank you very much. And remember, see you in the Barcelona meeting that will be in 2022. And again, thank you very much, and I will be open to answer any question that you decide.
So thank you, Fernando, for sharing your results with us. I think, or I hope the audience still has some time because we already received several questions for you. Perfect. So I will just start with the first one. I think this was still for Marcus, but I'm sure you can also answer it. So the question was, is migration of protecting groups detected between thiol groups?
Migration is yes. For instance, you see my screen? No? Okay, in the case of the seed, sometimes at the beginning, we see that the migration, the seed from one thiol to the free thiol. Means the migration is presence in all the cysteine. Remember that the oxidation is a thermodynamic process, and they have several intermediates, and we have to push the reaction to the more stable or the more stable product. But yes, migration means in between two sulfurs. The migration is reversible. The problem is, for instance, in the case of the ACM, we have migration of the acetaminomethyl from the sulfur to a tyrosine to a tryptophan, and this is irreversible migration, and this converts inside products.
Okay, thanks. So just for your info for the following questions, your presentation is visible again for the audience. So if you want to switch slides, okay, it works again. Okay, then.
Yeah, I was about migration. I was mentioning about this. Here we have some migration, and also we have the carbamate. Means in cysteine, we have always in the research we have to be patient. Means don't be depressed if the first SPLC is terrible. Means don't be depressed. Means sometimes in cysteine there are this kind of migration, this kind of thermodynamics, and then, as you can see, in 5 minutes we can suicide ourselves. After 1 hour and a half, we realized that it was wonderful. After overnight, was perfect.
Thanks. So the next question is, does NCS deprotect cysteine ACM and subsequently affect disulfide bond formation?
Yes, yes, yes. The NCS removed very nicely the ACM and is removed and oxidizing at the same time. No doubt.
Okay, thanks. Then another question, how is dimethyl thiazolidine stable to cleavage?
It's sequence depending. In some, I show a very easy example. In 1 hour was gone, but in some cases, in the cyclic peptides, much more difficult. I would say that in cyclic peptides are stable. In linear peptides, depends of the sequence. In some cases, you can remove, and in some cases, you need to boil in TFA or to use trifluorometanosulfonic acid or HF. But it's sequence dependent. But in cyclic peptides, of course, probably if you boil in TFA, also will be able to remove. But okay, it's not the best method to boil peptides in TFA. But in cyclic, I would say is rather stable. In linear, you can remove.
Okay, so 2 more
but
questions.
Remember, I'm sorry, then the methoxybenzyl, the one also is a new version of the I'm sorry, it was in my last slide. The dimethoxybenzyl. This one. Yes, this one is totally labile in the presence of the of TFA.
Okay, then 2 more questions, if you still have time for us.
Sure.
So, are the chemistries known with cysteines applicable with penicillamine? If not, what are the main differences between cysteine and penicillamine, also with respect to protecting group stabilities?
Okay, penicillamine is a cysteine with 2 methyls in the beta carbon. Here we have 2 methyls, and this means that everything is much more demanding. We didn't have time to prepare our C derivative of penicillamine. We'll prepare, but for sure the ester butyl is totally stable in the penicillamine, and our seed will be much more labile in the penicillamine. Means the 2 extra methyls introduce restriction and introduce stability. For instance, we didn't talk about that, but we know that the ADCs, antibody drug conjugates, is some of them or most of them are the conjugation is through a cysteine like moiety. One of the problems of the ADCs are the lack of stability. And right now, some of the ADCs, the antibody drug conjugates, are being constructed using dimethyl moieties of the cysteine. They are using these penicillins. Okay, means everything takes the same, but is a most demanding. But PHACM we used in the past, and you can remove from the penicillamine, and I am pretty sure that DPM also, trityl also, and the seed, I am pretty sure that we'll be able to remove from the penicillamine.
Great, thanks. So now the last question. What is your experience with deprotection of TRP-BOC? Do you still see TRP-COOH after 1 hour cleavage with TFA TIS water 95, 2.5 to 2.5?
Mostly of times, yes. Yes. Again, is sequence dependent. It's sequence dependent. Mostly of the time, yes. And again, this is the typical case that even myself, and I am working with the cysteine for 40 years, the first thing, oh, the synthesis was terrible. Then somebody say, but this is a tryptophan. And when you have 2 or 3 tryptophans, this is a big mess. They cute after a few minutes. Means the idea is to leave, to put some 50 millimolar sodium bicarbonate and to leave overnight, and the next day, miracle, single peak.
Okay, thanks. So this was now the last question. Thanks a lot. The feedback which we already received from the audience is great. So also from the audience and from our side, it was really a pleasure to have you with us. Thank you so much for your time, for your interesting talk.
Thank you to you, Marcus, Thomas, and if somebody wants my slides, you can send them my slides. It's not any problem.
Yeah, definitely we will. Yeah, so with this, we would already like to close our online workshop. As a follow-up, we will provide the recording, and as Fernando mentioned, if you're interested, we will also distribute the whole presentation and also a summary of the Q&A for you. Thanks again for joining us. Thanks again to all our speakers, and also a big thanks to Dr. Klaus Helm, who is always taking care of the technical support, but who is always hidden. So we hope you had as much fun as we had during this online workshop. We are looking forward to meeting you for the next workshop next year. And with this, I would already like to say, yeah, enjoy the Christmas holidays, have a happy new year, and see you soon for the next workshop.
See you. Bye-bye.
Bye-bye.
Bye.
Bye-bye.